Hello, my name is Etienne Tardif, and today I'll be presenting practical hive monitoring for the series Beekeeper as part of the 4th International Bee and Hive Monitoring Conference. As I said, my name is Etienne. I live up in the Yukon, which is east of Alaska, and yeah, I'll be briefly talking about microscopy, hive observations, and how I use my hive sensor to help me develop a better knowledge on beekeeping up north, because there wasn't much information here prior to me starting beekeeping. Yukon, 40,000, I guess more moose than people. Subarctic climate. We've got a mixed boreal, prairie, alpine, subalpine type environments. No agriculture, very few beekeepers, and we're actually non-regulated, so it's up to us to self-regulate and manage how we beekeep up here. My bees, 11 colonies in 3 bee yards. I use polystyrene hives, mostly Carniolan queens from southern BC or California. I do have some of my hives with my own raised queens. My typical survival rate is, I'd say, 75% to 95%. I did have a few nosema issues a few years ago that brought my overall winter rate down. Mite counts when I do washes are 0, so I tend to just use OAV to give me an indication of mite numbers, and also I treat all my first year hives. So why do monitoring? One, beekeeping is local, so if you don't have much information on your area, then collecting data is really important. So it helps you with determining the local approach and practices, timing, pooling information and sharing with other beekeepers, improving your yields, and then understanding the bee cycles and the typical stress-related ones. So I'm an engineer. I do reliability engineering, process type stuff. So data I use a lot in my work, and I typically need data relating to something else. Hence the reason I collect multiple points. So I've got internal temperatures, humidity, hive weights, external weather. So via my weather station, I do inspections. So it gives me an idea of what's going on in the hive. Disease and pest monitoring. So mite counts, nosema checks. What's going on from a forage perspective. So I do dog walks. So I take notes on what's blooming and when. And then heat loss, I have an IR camera. I've crunched some numbers, some basic engineering calculations to try to figure out what goes on in that hive in the winter. Field observations, just this quick section about the importance of actually knowing what's going on in the hive while you're collecting your data. So this is just an example of something part of my 5-minute inspection. So screen bottom boards, I have them all on all of my hives. And it gives me quite a bit of information, especially around mites, chalk brood, the expansion of the hive, so fresh wax, brown cappings, uh, and various things. It's just an example of using a $20 pollen collector and my field observations to develop my bloom calendar for this area. Just some more examples of having a camera out in the field and recording what you see. So on to microscopy. So microscopy, I found is a very useful tool. So over here, I've been doing my own nosema checks for the last 4 or 5 years, checking the bee guts, observing different pollen, yeast spores, rust spores, nosema, so positive, negative, high mortality, low mortality. I have a lot of honeydew honey in this area, so you'll start seeing a lot of honeydew trace elements in the bee guts that show signs of nosema. Is it a connection? It may be. There's probably more to it than just that. My bees do tend to collect a lot of rust spores later in the season, especially in mid to late August, and they do pack it in. So I have a feeling it does have an impact on my brood rearing, especially developing those winter bees. And I've been feeding pollen patties from early August and been seeing positive results on that. My disease monitoring tracking sheet. So I do nosema, varroa. Occasionally I'll add comments around chalk brood if I see that. Here it's just my ranking system. So when I do my monthly checks on my winter hives to see how many dead bees are out front of each hive, I do take samples off of each of these landing boards, and then I do a spore concentration because I follow the exact same procedure for each one, and it just gives me an idea of what's going on. Typically, high spore count and high mortality equals a hive that will make it past late May to June. But my weather station, I've developed a measure called cluster degree hours. And it's basically a cooling degree hours or something similar to a growing degree day, but I've brought it down to the hours for hourly data and compared it to 8 degrees Celsius, the temperatures at which I guess bees typically start clustering or don't leave the hive. And then this is just a cumulative curve of that measure over time for various locations in North America. Using the same weather data, I developed some forage intensity indicators. So temperatures over 8 degrees C is this blue area. So this is where the bees could be foraging for pollens. 16 C and above. So that's where most likely foraging for for nectar would occur. These green bars are acceptable daily forage hours. So it gives me an idea of how many forage hours per day, per week, per month for the season at various times versus the weather. And like I mentioned before, cluster degree hours, CDH. Down here is just similar, looking and comparing wind data and rain data. And the last point I do with weather is get an idea of, I wanted to understand what are the best queen rearing periods. So I took 10 years of data for my area, and then I stacked it and then compared it to 20 degrees Celsius. And then you can clearly see early June for the last 10 years has been terrible. And then periods C and D, so late June, early July would be the best because they still give you time to get that hive ready. But clearly from mid-August, there's a drop in temperature. And that's the typical end of the season. So now on to hive temperatures and weight scales. $30 sensor. And with this one, along with my weather station data, so the red line is that internal sensor. These are all my activities, main activities during the season. And this brown line is the outside temperature. And then this orangey line is the daylight hours. So you can see that I installed the Nook. I added a second box. Temperature is a lot easier to maintain when the cluster can surround the whole brood nest. It's flat at 35 degrees C. Around the end of August, temperature starts dropping. It flatlines around, say, 15, 17 degrees Celsius. After the solstice, it starts climbing up again. And then the cycle repeats itself. So with these temperatures and then this weight scale, It helps with the timing of when to feed, how stable is the queen still laying, all that type of stuff. So for the weight scale, basically, it helps you identify, for me, the most important one was the nectar flows. And the nectar flows, there's two. There's a June one and a mid-July to late July one. And over the last 3 years, I guess the June one has been bigger and more consistent than the finicky fireweed July flow. This is just a chart, again, visualizing data to try to get an understanding of what triggers a fireweed flow. Visually, my fireweed patches, acres of them, are visible and flowering, and I was trying to understand what created this weight gain. On to overwintering strategy. So I purchased a bunch of these sensors and I put some in a double and a single. So my single had 4 sensors across the top of the bars, side walls, and in the center, about a third to the back of the hive. And I had one at the entrance. And I did something similar in a double hive, a double brood chamber hive. And it was to help me understand the impact of insulation, condensation points, so dew points inside the hive, and also cluster location. So this scatter chart here is internal temperatures versus external temperatures in a double brood chamber hive, and you can see that even at really, really cold temperatures, the coldest internal temp is -5, and that's in the opposite corner from the cluster on the back side of the hive. And most of the winter was spent in the 10 to 20 degree range. Another visual check, knowing where the cluster is, observing the hoarfrost at the entrance on really cold days, you can almost deduct how the air is flowing through the hive. So the cluster was typically just above the entrance at the front of the hive. So hot air rises, it cools, so it drops, it condenses some of the water out on the backside here likely, and then it flows out naturally out of the hive. So the bees have to do very little, I guess, beating of their wings to get that air to move. All they have to do is manage heat, release heat to get the air to move. This here was just using the IR camera to understand heat loss. And you can see that these plastic tabs are heat sinks, and the location of these sensors are also infiltration points. And like you'll see in the next slide, they're also the points where you get the most humidity and condensation in this hive. So I've cut these plastic tabs off now and taped the ends so that the sensors can sit on top of the bars and not cause infiltration points into the hive. This here is just an example of my winter model. I've got 3 levers: health, so nutrition, stressors, deficiencies type things, and diseases; food, so the storage and the amount of honey, so are they going to starve? It also impacts the thermal mass inside the hive. And then over here, I've got the hive itself, the construction of it. So you've got insulation, you've got the volume to cluster size, and then ventilation. So where active would be a top entrance, and passive would be just a normal lower entrance. Over here, a bit of engineering physics. I modeled 4 scenarios, so wood, solo insulated, 2 hives stuck together, 1 stuck in the middle with 2 hives on either side. So just by crunching these numbers and simulating based on some of the actual values that I had, you can see that a shared wall is better. The importance of the bee to volume is critical. Tape those seams because they create heat loss and they create condensation points. And nooks can be overwintered north of 60. because that nook that I overwintered did well. It had plenty of stores left at the end of the season. Almost done. This is just an example of me collecting temperature data over time. So these are weeks, the months, and then the weeks. We've got our cluster degree hours. This time I actually compared it to 10 degrees Celsius for my double brood hive and a single brood hive. I calculated the meta rate based on the coldest internal temperature and the cluster size. And then with that, I used it to back calculate an estimate of honey consumption. So just to finish off, what this did was it allowed me to confirm that a weak hive is relative to the number of bees and really to the volume. So up here, what it does is I can rear queens in July, and if they don't get big enough, I can actually just overwinter in a nook. If they're big enough, I can put them in a single. And if they were an early June type queen or split, I can do a double if they get there. So it just gives me flexibility. Last point, again, it just shows the energy requirements of insulated versus uninsulated. If the nest had to bring the temperature versus exterior temperature to 35 degrees Celsius. So this is just an example of how you can use weather data to your advantage. And then if you have no questions, then hive monitoring probably is not for you. But if you have questions and you're looking at getting some answers, then it's actually a neat tool that will help you dig deeper and learn more about beekeeping and the bees in biology. And finally, for me, it was all about sustainable beekeeping and growing my numbers and actually making it a viable hobby and potentially business up here in the north. Thank you.